What is Inventor? Well, this may seem like an obvious question. It's a 3D CAD tool, right? Well, that's true, but there are a few things you need to know that make it different than other systems you may have used in the past, like AutoCAD. Inventor is a parametric, feature-based system that allows you to create 3D parts, assemblies, and 2D drawings. Parametric modeling is a bit different than AutoCAD, which is object-driven. What I mean is, in a parametric modeler, everything is controlled by either parameters, dimensions, or relationships. For example, if you want to move the position of a hole that's in a block, in a parametric system, you would change the dimension or relation that controls its position. While both systems do get the same job done, there is a reason why a lot of CAD users have switched over to parametric modeling. You actually get much more power and flexibility when using the parametric system. The parameters and relationships you set up allow you to have control over something called design intent. The term design intent basically describes the way your design will behave depending on the way you use parameters, such as dimensions and relationships, to design it. Here's an example. I'd like to center this circle within the rectangle. I know the rectangle is 4 inches by 6 inches. One way to center the circle is to dimension it 2 inches from one edge and 3 inches from the other edge. That centers the circle on this rectangle, but does this capture my design intent? Well, let's see what happens when I change the size of the rectangle to 7 inches by 8 inches. As you can see, the circle is no longer centered. So no, this doesn't capture my design intent. So how can I center this hole so that no matter what size the rectangle is, the circle will always be centered? In a parametric modeler, it's also possible to use relationships. Let's get rid of these dimensions. To create a relationship that centers the circle, I'll use something called constraints. But don't worry, all of these concepts are covered in detail in the upcoming lessons. Once the constraints are added, no matter what the size of the rectangle, the circle will always be centered. This is just one example of the countless ways to capture your design intent when modeling in 3D. As I mentioned, we'll talk much more about design intent and these geometric relationships throughout the course. You can see how modeling in a parametric environment can be very powerful. The other big advantage of this type of system is that you also get something called associativity between your parts, assemblies, and drawings. Meaning, if you make a change to the design of a part, the change will take effect in any assemblies that it's a part of, and its 2D drawing will update automatically as well. This associative behavior saves you lots of time when you make design changes, so that you only have to make the change once and all associated items will automatically update. Before you get started learning the fundamentals of creating parts, assemblies, and drawings, I'd like to take a few minutes to introduce some important areas of the Inventor interface that you will be interacting with during the remainder of this course. This is the interface for creating a part model, but it is also very similar to the interface for assemblies and drawings as well. An area that remains the same between all three interfaces is this large blank area in the middle of the screen, called the design window. This is your working space where you graphically interact with your parts, assemblies, or drawings. The other window that remains constant between all Inventor document types is the area on the left called the browser. This area will display all of the different sketches and features that go into creating the final part geometry, as well as the origin and default reference planes in 3D space. Most parts are created using a combination of sketches and features that are built on top of one another, so the browser is where each of these are shown after they're created. The browser will have slightly different information for assemblies and drawings, but in all cases, this window is a method to interact with the items shown in the design window. I'll go into much greater detail of how to use both of these areas throughout the course. Next, focus your attention to this area above the design window. Inventor organizes its commands, features, and tools in a ribbon-style interface, similar to Microsoft Office documents like Word or Excel. The different tabs organize the commands and functions based on the type of category they fall into. Each of the tabs are organized into something called panels, which groups similar tools together. Inventor does a great job of showing you tools that are relevant to what you're working on. As you can imagine, there are literally hundreds, if not thousands, of different functions available in the software. The interface will change to show you the tools you need based on what you're doing. For example, right now there are no sketch tools showing, but if I start a new sketch, the interface changes to include a sketch tab on the ribbon, along with all of the different sketch tools. If you need a little help from Inventor about a particular tool, just hover your cursor over it for a moment, and the pop-up gives you some more details. Also, notice the letter that appears in parentheses next to the tool. If you like using hotkeys, you'll find the default hotkeys for many of the functions here in this window. We'll stay away from hotkeys in this course for the sake of clarity, but once you get more familiar with the tools you use all the time in Inventor, hotkeys can make you a much faster user. Finally, take a look at the status bar on the bottom of the screen. If you're ever unsure about what input Inventor needs from you for the function you're working with, it will show up here. If you have multiple Inventor files open, you can toggle between them using these tabs. You can also split the window to see them at the same time, or cascade the windows by clicking the menu button in the bottom right and selecting how you would like to tile the windows. On the right side of the status bar, there's some other interesting info. If you're in a sketch, Inventor tells you how many dimensions or constraints you'll need to fully constrain your sketch, and the number of occurrences, or in other words, the number of parts showing on the screen. This will be more relevant when we talk about assemblies. The other number tells you how many Inventor files you have open. The final area on the screen that I want to mention is the area on the right of the design window. The view cube and toolbar here provide different ways of zooming, panning, and rotating in the model. Another useful tool in Inventor is the marking menu, which is accessed by right-clicking anywhere on the screen. It contains various useful tools depending on when and where I right-click. I often use it to quickly access sketching or feature tools, accepting changes, or modifying my view of the project. Right-clicking also brings up a drop-down menu, offering familiar tools and settings depending on what is selected in the software. If my interface looks a little bit different than yours does, don't worry. I've changed the color scheme to make the videos a little clearer. To get to this option, go to the Tools tab and select Application Options. If you go to the Colors tab, you can see the different default color schemes. I have mine set to Presentation and the background set to one color. But it is up to you to decide which scheme you prefer, and in no way does the color affect the overall model. In the following videos, I will show you some of the common methods used to navigate through the design window and access the different views of your Inventor project. Throughout this course, I'll be zooming, panning, and rotating to navigate around the models. So I want to make sure you have an explanation of how I'm doing this here in the beginning of the course. Now, before I tell you about all of the navigation tools here on the right, I want to show you how to do the majority of your zooming, panning, and rotating directly from your mouse. Some of these tools give you additional control, but using the mouse is a faster method to use a lot of the time. First, let me show you how to pan the model. All you have to do is press and hold the center mouse button or scroll wheel. With the center button depressed, just move the cursor on the screen. Next, I'll look at zooming in and out. This time, with the scroll wheel, all you have to do is roll it towards you to zoom in and away from you to zoom out. This might be the opposite of what you're used to if you're coming from AutoCAD, but it will eventually become second nature to you. One thing about zooming: when you roll the mouse button to zoom in, Inventor zooms in on the position of your cursor. New users sometimes have a hard time with this and end up zooming the part outside of the design window. I'll show you what I mean. Say I want to zoom in on this corner of the part. If I leave my mouse in this spot on the screen and keep zooming in, notice the part eventually leaves the design window. This is because the mouse is positioned over the background immediately after I start zooming in, which means I'll be zooming in on that spot in the background and not the model. If I want to keep this from happening, I must relocate the cursor to the spot I want to zoom to every few seconds while zooming in. One last tool I want to mention is Zoom All, which can be helpful if you somehow lose the part in the graphics area. To use it, you can simply double-click the mouse button and the part will return zoomed to the middle of the screen. If you like hotkeys, you can press the Home button on the keyboard, located near the Delete button, for Zoom All as well. So, to recap, you can pan by holding the middle mouse button down. You can zoom in by rolling the scroll wheel towards yourself while adjusting the cursor every few seconds to zoom into that area, and zoom out by rolling the middle mouse wheel away from you. If you zoom out too far, just double-click the middle mouse button for Zoom All. Finally, you can rotate the model using the center mouse button while holding down the Shift key on the keyboard. With both buttons pressed, notice the model reacting to each direction I move. Many new users can have trouble getting the desired result from rotating. They might start using circular motions with the mouse until eventually it ends up in the right spot. My advice while getting started is to simply limit your rotate command to vertical and horizontal directions. Here's what I mean. Watch as I press the middle mouse button along with Shift and move the mouse in only the up and down directions at one time. When I'm finished rotating up and down, I'll release the buttons, press and hold Shift and middle mouse button again, and move from side to side. Again, this will all become second nature with practice, but these tricks should make it easier while you're getting used to it. Once you're comfortable using the mouse to zoom, pan, and rotate to get around in your model, you may find that the tools in the View Cube and navigation bar give you more refined control, and in some cases, one-click access to particular views. First of all, in the upper right corner of the design window, you'll find the View Cube. This cube lets you click on its faces to look straight on with the corresponding view of the model. You can also click the small arrows that appear next to it, as well as the arrows that face clockwise and counterclockwise to spin the model on your screen. If you click and hold down on the cube with your left mouse button, you can drag the cube freely to rotate the model. From here, you can even click on the edges of the cube, as well as the corners to rotate to the corresponding area of the model. Notice when I hover my mouse near the cube, there's a home icon that quickly orients the model into an isometric view, where you can easily see the top, front, and right views. Just below the View Cube, you'll find the navigation bar. This bar has more navigation tools to help you zoom, pan, and rotate. I'll talk more about this steering wheel tool a bit later. Just below that, you'll find a hand tool that you can use to pan. Just click the tool and click again to grab the screen and pan around. Below Pan is a zoom tool, which has several options. You can use the drop-down button to zoom, which behaves similar to the Pan tool, Zoom All, Zoom Window, or Zoom Selected, which waits for you to select a face or feature to zoom all the way into. The Orbit tool is another method for rotating the model. When you select it, a target appears on the screen, which serves as a center for the rotation. If I click in the inside of the target with my left mouse button, I can rotate the model freely about the center. As I move my cursor over the different parts of the target, notice how the cursor changes slightly. If I hover over one of the horizontal lines, I can click and rotate the model from left to right, and any vertical mouse motion doesn't affect the rotation. Likewise, if I click a vertical line, the rotation can only move up and down. Left and right mouse motion doesn't affect it. You can also click on the circular part of the target to spin the model clockwise or counterclockwise. Now, the last tool on the navigation bar is called View Face, also known as Look At. If I hover over it for a moment, notice there's a hotkey for this tool, which is the Page Up button on the keyboard. This is a good one to remember, since Look At is a tool you'll use often. To use it, just press the icon or the Page Up hotkey if you prefer, and then click the face you want to look at, and Inventor will look straight on with it. This can also be accomplished using the marking menu. Simply right-click the desired face and select the Look At icon. At the bottom of the navigation bar, notice you can customize which tools show up in case there are other tools you want to add to the navigation. It also lists their hotkeys. So, for example, you could add the Zoom All command to the toolbar, or if you're like me and prefer using hotkeys, try to remember that the Home button on the keyboard or double-clicking the middle mouse button performs the same function. Hotkeys will become more second nature as you use Inventor and will definitely help you get your job done faster. These are the majority of the tools you will need to navigate through the Inventor interface. In the next set of lessons, I will go over basic sketching techniques used to create an Inventor part. Part designs in Inventor are made up of a combination of building blocks called features. There are two broad types of features in Inventor: sketch-based features and placed features. Every 3D part in Inventor begins with a sketch-based feature, such as an extrude, revolve, sweep, or loft. As you might have guessed, a sketch-based feature starts with a 2D sketch, and that sketch is the basis for creating the 3D geometry using the features I just mentioned. Sketches are created using simple tools, such as lines, rectangles, and circles, and can be defined very precisely using dimensions and something called constraints. I'll cover both of these things later in this section, but before I dive into that, I first need to show you how to start a part and create sketches. You've learned that you can create parts, assemblies, and drawings in Inventor. Any of these file types can be started by selecting an icon here or by going up to the ribbon and pressing the New icon. When I do, a window appears that prompts me to select a template. Templates have predefined settings, such as units of measurement, among other options. And notice that there are templates for both English and metric units. If you find that you always change settings as soon as you start a new file, you can create personal, customized templates with those changes already in place. For now, though, I'll select the standard IPT template and click Create. When I do, Inventor opens a blank part file, and I want to start a new 2D sketch right away. To do that, I'll go to the 3D Model tab on the ribbon and click Start 2D Sketch. And then, since a sketch must always start on a plane or object face, select the XY plane to start working. I'll start drawing a line by selecting its icon on the ribbon and then clicking to place a point. As I pull away, notice that since I chose an IPT template for the file, the units are shown in inches. I want to use metric units instead, but rather than starting a new drawing with a metric template, I can instead simply modify the document settings. I'll go to the Tools tab on the ribbon and select Document Settings to bring up the Document Settings dialog box. From here, I'll navigate to the Units tab and then set the length units to millimeters and the mass units to grams. I'll click Apply and then Close to accept the changes. Now, when I start a new line, the units displayed are in millimeters. With the units set, I'm ready to start modeling, but what do I sketch first? You might have an idea of what the part should look like, but how do you get there when you're starting with a completely blank screen? Well, think about design questions like, what features should I use? What should my sketch look like? Or how should I dimension it? There is no single right answer to these types of questions, but to give you an idea of how to approach these questions, I'll show you a few completed parts and how they were created. I'll switch to this completed pin part, and notice in the browser on the left that the pin is simply made from a combination of simple extrude features. And if I expand them, notice that each of the features contains the sketch it was created from. The pin here is a simple part, but you can also break down more complicated looking parts into simple shapes. I'll switch to this bracket part, and to get a better look at the bracket's construction, I'll move the End of Part icon in the browser to hide the fillet and hole features. As I walk back through the part, notice that the bracket is made of a combination of 3D extrusions, similar to the pin, with a basic rectangle as the base. Not so intimidating at all. I'll expand and select the sketch, and you can see that it is a thin rectangle that defines the height and length, so the extrude defined the width. But would it have been a better idea to sketch a large rectangle on the bottom that defined the length and width, and then extrude it up to get the height? The short answer is maybe. It's up to you. Both methods will create the same geometry, but I will mention that your choice here can affect how the part updates and interacts with other parts in the assembly. With all that said, I'll switch back to the blank part file, and in the next few lessons, I'll walk through several approaches for sketching and designing parts, as well as go over how to use features to turn those sketches into 3D geometry and create the pin I showed earlier. Sketching is the basis for all the geometry in a parametric modeler, like Inventor. So, in order to create the pin part shown in the last lesson, I'll need to start with a sketch. I'll select the Start a 2D Sketch icon from the 3D Model tab of the ribbon, and then select the XY plane. All of the sketch tools are found on the Create panel under the Sketch tab, with the most common tools like lines, circles, arcs, and rectangles immediately available. I can expand the drop-down beneath each tool to find additional, more advanced tools, such as splines or ellipses, and some commands such as arc and rectangle have multiple ways to use them. The pin part, if you remember, had a hexagonal head and a non-threaded cylindrical post. To get started then, I'll sketch the pin head as the base and build the post later. You can draw just about any shape using the line tool, so I'll activate it from the ribbon and click anywhere on the screen to set the starting point. At this point, I can freely drag my cursor to place the line, or use the boxes to input an exact length and angle. The line I'm drawing represents one of the bolt's faces, so I'll type 30 for the length, press the Tab key to switch to the angle input, and type 60 before pressing Enter to confirm. Inventor adds a dimension with the values I just typed. And when I pull away, notice that the line tool is still active, allowing me to keep sketching lines without having to go back to the Create panel. For the next segment, I'll keep the same length, but change the angle to 120 degrees. I could keep sketching lines this way until the profile is closed, but for common shapes like rectangles or polygons, Inventor has tools that can create the shape in one step. To exit the line tool, I can right-click and select OK in the marking menu, or simply press the Escape key. I'll then select the lines and press the Delete key to clear the screen. But note that you need to be careful when deleting objects, because the sketch's origin can be selected and deleted as well. Since I want to draw a polygon, I'll use one of Inventor's built-in tools. I can find the Polygon tool by going to the Rectangle dropdown and selecting Polygon. When the tool activates and the dialog box appears, notice that I can sketch a polygon in two ways: inscribed or circumscribed. Choosing the Inscribed option lets me draw the polygon as if it's inside an assumed circle, and choosing the Circumscribed option draws the polygon around an assumed circle. It's hard to tell the difference between the polygons, so I'll delete them. And quickly draw a circle to show you what I mean. I'll reactivate the Polygon tool from the ribbon and select the Circumscribed option. Notice that when I place a point at the circle's center and drag to its edge, the polygon is around the circle. If I select the Inscribed option instead and drag to the edge, the polygon is inside the circle. I'll click to place the polygon, keeping the circle as its framework. As you can see, there are a large variety of tools and methods to approach sketching. So, I recommend exploring the sketch tools on your own to get comfortable with all the shapes available to you. In the next lesson, I'll show you how to control a part size and position using dimensions. Dimensions and constraints play a critical role in defining geometry and help you precisely control the sketch with either size and spacing values or geometric relationships. As you saw in the previous lesson, Inventor lets you input values to create dimensions as you sketch, but this isn't the only way to add them. To show you what I mean, I'll dimension the circle and polygon sketch here using the Dimension tool. At the moment, notice that the shapes are free to move around and change size, meaning they are unconstrained. In order to fully constrain the sketch so that it can't move anymore, I'll need to add 4 dimensions to the sketch, as you can see on the status bar at the bottom of the screen. The 4 dimensions referenced here means that there are 4 degrees of freedom in this sketch that will need to be locked down before it will be fully defined. To start, I'll first control the sketch's size, so I'll go up to the Constrain panel in the Sketch tab and activate the Dimension tool. Since the polygon and circle are connected, I can define both of their sizes simultaneously by clicking on the circle's edge, typing a value, say 60, and then clicking the green check to place the dimension. Like the Line tool, the Dimension tool remains active, and I can continue adding dimensions if I want to. With the shape size now defined, the status bar now reports that 3 dimensions are needed in order to fully constrain this sketch. Remember how a moment ago I was able to change the sketch's size and location by dragging around the sketch? If I try and drag the sketch now, notice that only the location changes. This is because the diameter dimension is now driving the geometry, meaning that it is a parameter for the model. This relationship between dimensions and geometry is the basis of parametric modeling, and means that if I want to change the sketch's size in any way, I'd need to edit this parameter. Since I can still move the sketch in the X, Y, and Z directions, I'll next need to dimension its location to fully constrain it. Since there's no other geometry in the file, I'll need to dimension its location relative to the origin. I'll restart the Dimension tool by pressing Enter. And this time, instead of selecting an object to set its size, I can select a point, like this endpoint, and another object, like the origin, and I'm able to set a distance between them. As I move the cursor on the screen, notice that Inventor switches the type of dimension I can place between vertical, horizontal, or aligned, depending on where my mouse is relative to the points. In order to lock in the Align dimension, I'll need to left-click while this icon is showing, or I can lock to any dimension by right-clicking and selecting an option from here. I'll select Aligned to dimension the diagonal distance between the points and set it to 80. The status bar updates to show that I need to add 2 more dimensions. I'll press Escape to exit the tool, and notice that I can still move the sketch in the X and Y directions. I'll restart the Dimension tool and create 2 more dimensions using the origin and a point to the side of it, then the origin and a point above it. With that done, the status bar reads as fully constrained, and I can no longer move the sketch geometry. It's generally considered good practice to ensure that every sketch you create is fully constrained before moving on to create features. And using dimensions is the most straightforward and rigid way to do this. In the next lesson, however, I'll show you another way to define sketch geometry by using constraints to control geometric relationships. You can use to relate sketch segments, model geometry, and the center point or origin of a sketch. Constraints are key to parametric modeling since they can be used to constrain sketches alongside dimensions but are more flexible to updates. For this example, I'll delete all existing dimensions. And you can see that the status bar says I need 4 dimensions. As I mentioned before, this doesn't mean numeric dimensions, but instead references the degrees of freedom in the sketch, and will decrease as I add constraints. Inventor has several different types of constraints, and I can find them in the Constraint panel on the Sketch tab. If I hover over the horizontal constraint, a tooltip appears, letting me know its use case and that it causes lines, ellipse axes, and point pairs to lie parallel to the x-axis, making them horizontal. Likewise, if I hover over the vertical constraint, the tooltip lets me know that it makes those same types of objects lie parallel to the y-axis. I want this hexagon to have a flat top edge, so a horizontal constraint sounds like it fits my design intent. I'll select the constraint, then select any line on the polygon, and it immediately snaps to horizontal. Horizontal and vertical constraints are some of the most commonly used, so I recommend you get comfortable with using them. Another common constraint type you'll encounter is the coincident constraint, and when I hover over the tooltip, it lets me know that it attaches points to other types of geometry. This constraint has many different applications, one of the most common of which is centering sketches. Remember when you started a sketch and picked a sketch plane? All of the default sketch planes intersect the origin, so it's good practice to draw from or center drawings on the origin. I want to center the sketch on the origin, so I'll select the coincident constraint, then select the center point of the circular sketch. I'll then select the sketch center point on the origin, and as soon as I do, the sketch snaps into place. Notice as well that the status bar changes from 3 dimensions remaining to 1. If for some reason you can't select the origin, or if it was deleted accidentally, all you have to do is click Project Geometry on the Sketch tab, and then expand the Origin menu in the browser to select Center Point. This will create a new center point at the origin of your sketch. I'm satisfied with my results so far, but what if I wanted to get rid of a relationship? To do that, all I'd have to do is delete the constraint. To make constraints visible, you can press the F8 key on the keyboard and then toggle them off again with the F9 key. With the constraints visible, I can click and move the flags to clear some space, or simply select a constraint, like this coincident constraint, and delete it from here. In addition to adding constraints through the tools on the ribbon, you can also add a coincident constraint by simply dragging and dropping geometry onto another reference. I'll undo the coincident restraint I just added, and this time I'll drag the center point of the circle over near the origin. An icon pops up, telling me that it'll add a coincident restraint, and when I release the mouse, it's added. Be sure to pay close attention to these small icons that pop up next to your pointer. If you don't, you may be creating constraints without knowing it, which can be frustrating when the sketch doesn't behave as you're expecting. The automatic constraint here with the current sketch was very simple, but as your sketches get more complex, so do the potential constraints. With that in mind, Inventor lets you add constraints while sketching to speed up this process. For example, I'll start the Line tool, place a point, and when I get near horizontal, a horizontal constraint icon appears near the cursor, letting me know that it will be automatically added if I place the line here. A similar vertical constraint appears if I move up, and once I've added a second point, you can see a perpendicular flag appears when applicable. These automatic constraints are extremely helpful when creating initial geometry. You just need to make sure that you want the constraints that are being added, so you don't wonder why you can't move a line as you want later. I'll undo the line placement and leave the circle and polygon's last dimension unconstrained for now, because while it is possible to fully constrain a sketch with just constraints, I'm not able to set the circle size in this sketch with them. If the idea of using constraints like this is confusing to you, don't worry. It will become much easier as you get more experience. And in the next lesson, I'll use both constraints and dimensions to fully constrain the sketch I have here. At this point, I've sketched some geometry, added dimensions, and used geometric constraints. While Inventor doesn't require you to fully constrain your sketches in order to create 3D features, it is generally considered best practice to do so. The reason for this is that it ensures that you, as a designer, have thought through the design intent and haven't left any of the features of the design to chance. So, knowing what you know now, what combination of dimensions and constraints can lead to a fully constrained sketch? You've already seen how you can just keep adding dimensions to fully constrain a sketch, but since dimensions aren't very flexible, you'll usually want to use a combination of constraints and dimensions in order to create the design intent you want. In the sketch here, you can see that there is only one dimension needed, and I can figure out what it is by either clicking and dragging the sketch geometry to see what moves, or by clicking the Show All Degrees of Freedom icon in the status bar, which brings up red arrows indicating how the sketch can move. Since the sketch already has some constraints, you can see that the only degree of freedom left is related to the size of the geometry. That is easily solved by adding a dimension, so I'll activate the Dimension tool and add a diameter of 60 millimeters to the circle. As soon as it's placed, Inventor tells me that the sketch is fully constrained. You might also have noticed that the lines changed colors from black to a dark blue. According to the color scheme I chose at the start of this course, any dark blue geometry is fully constrained, and any black geometry still has some degrees of freedom. If the color difference is hard for you to see, you can change the color scheme by navigating to the Tools tab and selecting Application Options. As you can see, I have my color scheme set to Presentation, but you can try out different color schemes to see which one works for you. Alternatively, you can adjust any of the colors in the scheme, background, sketch, or otherwise, by clicking Customize Schemes to bring up the Color Scheme Editor, and then clicking a color swatch to change its value. I'm going to stick with the Presentation color scheme and its defaults throughout this course, but keep in mind that your workspace is fully customizable. Since my sketch is now fully constrained, I can confidently add 3D features, knowing that the design is consistent, reliable, and finished. An extrude, in relation to 3D modeling, describes the process of taking a two-dimensional profile and making it three-dimensional by giving it some thickness. A simple example of this would be taking a circle and making it into a cylinder, or turning a square into a cube. I have here the finished sketch for the pinhead, and I can extrude this sketch without exiting sketch mode. I'll head to the 3D Model tab, find the Extrude tool on the Create panel, and click on it to bring up the Extrude dialog box. Since I only want to extrude the hexagon sketch, I'll select the hexagon instead of both the hexagon and the circle. As a side note, you don't need fully constrained geometry to create extrudes, but you do need to have a closed sketch profile. I can control the extrusion depth by dragging this arrow or by inputting a distance value here. If you don't care about the exact depth, clicking and dragging the arrow is a quick and easy way to explore different scenarios. And notice that the preview updates with all the adjustments I make by adding 3D material to the sketched base. Currently, the direction option is set to default. The default option simply means that I want to take my profile and extrude it in a single direction using a specified depth. I can flip the direction by clicking the flipped icon here, or add material evenly on both sides of the sketch by using this Symmetric button. When using Symmetric, the distance value represents the total depth, not the depth on each side, and Inventor takes care of splitting half to each side. If you need to add more material to one side of the sketch than the other, you can activate the Asymmetric option. This allows you to specify a unique depth for each side, as well as different end conditions for each direction. I'll switch back to using default and type in an extrusion distance of 50 millimeters. The 2 icon here lets you extrude up to a reference rather than a set distance. But since I don't have existing geometry to reference, I'll leave it set to 50 and press OK to end the command and create the extrude. If you take a look at the browser window on the left, notice that the extrusion feature is there instead of the sketch. This represents the feature I just created, and if I expand the feature, the sketch is nested underneath it, since the sketch's geometry drives how a feature looks. A solid bodies folder was also created, and if I look inside, you can see that there is a single solid body shown that I can expand to see its browser history. Understanding these browser relationships is important because the browser serves as a history of all the features and sketches that you've created, and is where you'll go later to check or modify your features. I'm satisfied with the pinhead I just created, so in the next lesson, I'll create the cylindrical post to complete the pin part. In this lesson, I'll show you how to create additional sketches using existing geometry as a sketch plane by creating the cylindrical post for the pin part. I'll click the Start 2D Sketch button and notice that instead of showing the planes for me to sketch on like before, Inventor just shows the icon next to the cursor to indicate that I need to select a plane. I'll move around the drawing area and notice that when I hover over a face, it highlights to let me know that I can sketch on it. The default planes are still available selections, but I'll need to select them from the browser this time to start a sketch on them. Since I want the cylinder to connect to the hex head, I'll select the large, flat front face that I want the cylinder to extend from, and Inventor reorients the model to look directly at the face while making the Sketch tab active. You can think of the sketch plane I'm in now as an infinite imaginary plane placed on that face that tells Inventor where in space the 2D sketch will be located. To show you what I mean, I'll sketch a simple rectangle next to, but not directly on, the part face. I'll then rotate the view, and since I drew the rectangle using a model face as a reference, the new sketch is in line with the face instead of the default XY plane that the hex head was drawn on. Sketching on faces is an indispensable function when creating connected geometry in your parts, as it lets you make sure they're connected, no matter how the geometry is oriented. I'll reorient the view cube back to the front view, and since I want the post to be attached to the pinhead, I'll delete the example rectangle and activate the circle tool. I want the cylindrical post to be centered on the pinhead, so I'll select the origin as my starting point and drag outwards to place the circle. The sketch isn't fully constrained yet, as you can see in the status bar, so I need to place a dimension to finish the sketch. I'll activate the dimension tool and set a distance of 30 millimeters for the diameter. With the circle fully constrained, I'm ready to extrude it to create the post. I'll activate the extrude tool, keep the default direction so that it extrudes in the same direction that the pinhead did, and then drag the arrow to about 75 millimeters to set the distance. I'll click OK to accept the changes and end the command. With that, another extrusion feature is added to the browser, and the pin is created. If this is your first time using Inventor, congratulations! You've just made your first part. What started as a simple idea was broken down, turned into a sketch, and pulled out into 3D geometry, all thanks to some commonly used design tools. In the next lesson, I'll go over how to edit what I've created here to account for any design changes or specifications I need to adhere to. Once you've created a sketch or feature, that doesn't mean that it's set in stone or permanent. You can always go back and edit the geometry once it's placed. New users often tend to delete features and recreate them from scratch when they need to make changes, but that's rarely necessary, so long as you keep the part structure in mind. Let me show you what I mean. If I decided that I want to change the shape of this geometry, the first thing I need to do is remember that the shape of a feature is controlled by its sketch. I'll click the plus sign next to the pinhead's extrude and edit the sketch nested under it by either right-clicking on it and selecting Edit Sketch, or by simply double-clicking the icon next to the text. This brings me back into sketch mode, where I can modify any of the dimensions or relations. I'll add 2 lines so the top of the polygon meets at a single point. But when I exit the sketch, notice that the extrude remains unchanged. This is because when I extruded the shape, I only selected the polygon profile. So while the lines were drawn on the polygon sketch, they aren't part of the extrude. I could further edit the sketch to more directly change the polygon profile, but the easier method of updating at this point is to simply edit the extrude feature itself. I can do this by either right-clicking the feature in the browser and selecting Edit Feature, or just like when editing a sketch, by double-clicking the feature's icon. I want to add the new geometry to the profile section, so I'll make sure it's highlighted. And now, notice that the lines I sketched form a profile highlight when I hover over them. Inventor allows you to select or deselect as many closed profiles as you'd like. So, I'll click on the highlighted geometry to extrude the profile. When I do, the preview updates and new geometry is added. If you ever make a selection that you didn't intend or need to remove a profile from your selection set, you can do so by holding down the Shift key and then hovering over and clicking the profile you want to remove. I'll make sure all the profiles I want are selected and click OK to accept the changes. As you can see, you need to have a firm handle on where changes need to be made in order to make good edits. A change to either the sketch or feature alone may not get you the results you want. I'll undo these changes. And next want to make some more permanent changes to the cylindrical extrude. I want to add this pin to an assembly later, and so need to match its dimensions to those I just received concerning the hole it will be placed in. The first change that I need to make then is to change the diameter of the sketch. Since I just need to change an existing dimension in the sketch and not add or remove any geometry, I can use a different method to make this edit. I'll select the cylinder in the graphics area, and in the shortcut menu that appears, you can see that I have options to edit the extrude, edit the sketch, share the sketch, or make the sketch visible. This menu is a great way to intuitively make edits, since you just need to select the geometry you want to change. But the option I want to use for now is Make Sketch Visible. I'll select it, and the sketch and its dimension appear in the graphics area. To update the dimension then, I'll just need to select it and change its value. I'll use 20 millimeters for now. I now need to update the feature to use the new dimension, so I'll go to the Quick Access toolbar at the top and click the Local Update icon. The geometry updates, so I'll hide the sketch the same way I showed it. Then click the geometry once more, and this time select Edit Feature. I'll change the length of the feature to 110 millimeters, and it looks good, so I'll click OK. I'm happy with the changes to the post, but now the pinhead looks oversized, so I'll select it in the graphics area, show the sketch, and change the diameter to 40 millimeters. I'll update the part so the model updates, hide the sketch, and then edit the extrusion to distance so that it looks more like a bolt. I'll set the length to be 20 millimeters and exit the feature. The pin is now done, and in the next section, I'm going to walk through building a more complicated bracket part with some common but slightly more advanced tools and techniques. Now that you've got a handle on how parts are generally created, it's time to up the complexity and discuss new features used in part creation. Since every part in Inventor is created using a combination of features, there are many possible approaches to your designs. Choosing the right approach for your model is called design intent. And as you make more complex parts and need to update them, you'll find design intent becomes more and more important. In simple terms, design intent means exactly what it sounds like, to put intent behind the design. That means that every feature, sketch, and dimension you have should serve a purpose and not be done simply because it's easy or works. With that said, you'll want to think carefully about how a part is made and set up your parts so that when they're edited, they update without trouble. For brand new users, figuring out which features and approaches to use can be overwhelming, so you may need to take a trial and error approach until you get the hang of working with CAD software. To show you the impact that design intent can have on a model, I'll switch over to Inventor, where I have two identical-looking brackets. As I switch between them, you can see that both have the same number of features, but one was made using mostly extrudes, while the other used something called a mirror feature. I'll roll back the end of part marker on both parts to after extrusion 2. You can see right away how the tabs were built differently. As I walk through the tree of the extrusion-focused design, you can see that a cut feature was used to cut out the middle of the long extrude, leaving me with 2 tabs. Alternatively, the mirror feature design created a single tab, and then used the symmetry of the part to copy it to the other side of the bracket. When considering design intent, it's important to weigh the pros and cons of a design path, especially if you're torn on which way to take. One of the most common considerations, then, is how can the design be edited? If, for example, I were to change the width on the base of both parts to 120 millimeters, what would that impact? I'll start with the mirror feature design, and when I increase the distance of extrusion 1, you can see that everything stays symmetric. When I repeat the same edit on the extrusion heavy version, however, the far side tab gets thick. This is because when I created the sketch that cuts out the middle area, I defined it based on a single side and middle distance value. To make this update the same way, I could change how it updates by defining the cut area from each side, rather than a middle distance. But what if the cut needs to be exactly 70 millimeters, no matter how large the base or tabs are? Changing the sketch would then go against the design intent of that feature. So, figuring out exactly what the key elements of a design are and how they should be built to capture that is the essence of design intent. As you become more experienced using Inventor and start to add more features to your tool belt, you'll find that the design intent will start coming more and more naturally. In the rest of this section, I'll work on expanding that tool belt by showing you how to build the bracket using the mirror method. Let's get started. In the last lesson, you saw how the rectangular base was the first feature built, followed by the tab and the cut. These could all be done in a single 2D sketch, but I prefer sketching and creating features in segments, so they're easier to find and modify later. With that said, I'll start a new part using a metric template. Then start a 2D sketch, and now come to my first decision point, picking the first sketch plane. If I choose the XZ plane, I can sketch the rectangle's top face and extrude it upwards to define the thickness. If I choose the XY or YZ planes, I can sketch a thinner rectangle of the front or right side respectively, and then extrude it outwards to add length or width. Since I'm going to be using a mirror feature later, having a plane in the center of my base will be helpful. So the easiest way to track that is to start on the XY plane and sketch the length and height of the base. I'll activate the 2-point rectangle tool, select the origin as the starting point, type 150 millimeters for the width, press the Tab key, then type 15 millimeters for the height, and press Enter to create the rectangle. I'll double-check the status bar to see what I need to do to finish the sketch. And notice that because I started on the origin and input dimensions as I was drawing, that the sketch is already fully constrained. I'll switch to the 3D Model tab, activate the Extrude tool, and since I want a plane in the middle of the base to help with the mirror later, set the base extrude to Symmetric. I'll set the distance to 100 millimeters for the extrude, and click OK to finish the rectangular base. I next need to sketch the tab feature, and once again, keeping the mirror feature in mind, can just create a single tab on one side. I'll start another 2D sketch, and this time select the front face of the base as my plane to make sure the tab is always positioned there, and can now sketch the tab shape. I want to use the top edge of the rectangle as the base of the tab, so I'll need to project it into the sketch. This is something that I find myself doing often, so there is a setting that I like to turn on to speed this up. I'll go to the Tools tab on the ribbon and select Application Options. In the Sketch tab, I'll make sure Auto Project Edges for sketch creation and edit is checked. Click Apply, then close the window. I'll click Undo from the Quick Access toolbar to undo the sketch creation. And this time, when I start a new sketch on the same face, you can see that the geometry is automatically brought into the sketch. To now sketch the tab, I'll activate the Line tool, place a point, move upwards, then press Tab and set the angle value to 75, and then press Enter. Next, I'll switch to the Tangent Arc tool, start the arc on the line's free endpoint, input a radius of 25, and press Enter to add the arc. Finally, I'll activate the Line tool once more to close the profile. And make sure to add a tangent constraint between the arc and the second line. Since I told Inventor to project the base geometry into my sketch, I'm now done with the tab shape, but notice that I still need 3 dimensions in order to fully constrain it. Instead of just adding dimensions to everything, I want to keep my design intent for the tab in mind. The first consideration, then, is that I want to center the tab on this face. Since construction geometry will be ignored by Inventor when creating features, I can use the construction line to add additional geometry without impacting the extruded shape. I'll activate the Line tool and select the Construction button on the Format panel. I'll then start a line at the center point of the arc and select the bottom edge's midpoint for the second point. I'll press Escape to end the Line tool and then add a vertical constraint to the construction line. When I do, it snaps to vertical and has its center positioned. I want the center of the arc to be 50 millimeters up from the edge, so I'll add a dimension and finally use an equal constraint to make the two lines the same length and fully constrain the sketch. I'm ready to extrude the geometry, and when I activate the Extrude command, notice that the vertical construction line is ignored when the profile is selected. I'll extrude the tab 15 millimeters, and notice that by default, Inventor will always extrude material away from the rest of the model. I'll then use the Flip Direction button to extrude towards the middle, and I'm done with the tab. Now that the tab feature has been created, I next need to make a cutout near the top of the tab that the pin can slide into. I can do this in Inventor with an Extrude feature. I'll just need to change its setting to Remove instead of Add Material. Just like all Extrude features, I'll need a closed profile sketch first. And to start the sketch this time, I'll simply click on the face or plane I want to sketch on and select the Start a New Sketch icon on the end of the shortcut menu. Inventor starts the sketch directly on that face, and since I enabled the Application option earlier, projects the outer edges as sketch entities. This profile will be a simple circular cutout, so I'll start the Circle command and snap the cursor directly on the arc center point so that it will be coincident with the circle. I'll type a value of 15 and press Enter to finish the sketch. As I mentioned earlier, a cut is simply an extrusion that removes material. So I'll go to the 3D Model tab on the ribbon and start by activating the Extrude command. I'll select the circle as my profile, and in order to remove material, go to the Output section and switch to the Cut option. The preview updates, and you can see the extrude direction changed so that material was cut away. Back in the Behavior options, you can see that I have a few options for setting the distance that I've only touched on before: Through All, To, and To Next. These end conditions are really helpful when determining the design intent of your extrude. And since I want this cut to always go through all geometry, no matter what updates are made, I'll use the Through All option. If, on the other hand, I were to give this cut a distance of 15, you can see that the cut still goes through the whole tab, but any change to the tab that would make it thicker than 15 millimeters would prevent this cut from going all the way through it. I'll switch back to Through All for now, and click OK. With the cutout created, I'm ready to replicate the tab to the other side of the base. If you're designing a part that's symmetric, like this one here, you can save yourself time by using the Mirror feature. This feature can replicate 3D geometry like individual features or entire bodies, and it can be found on the Pattern panel of the 3D Model tab. In this lesson, I want to put a copy of this tab on the other side of the rectangular base, so I'll enable the feature. In order to mirror 3D geometry, I first need to select a plane or flat face to use as a reference. I'll select the Mirror Plane icon in the dialog box to enable selection, and can either use model faces, one of the default planes, or even a custom plane if one exists. In this case, if I hover my cursor over the XY plane in the browser, you can see that it passes through the center of the part. This is no coincidence. If you recall back to when I created the rectangular base, I used the Symmetric option to extrude it, which added material evenly to both sides of the sketch plane I started on, the XY plane in this case. This was a good strategy, since now I don't need to create any additional planes or geometry to mirror across. I'll select the XY plane, and the tool immediately switches to a Feature Selection option. I'll select both the tab and circular cutout features to mirror, and a preview of the new geometry appears. I'll press OK, and the features are mirrored. The design intent here is clear, because any changes made to the original tab will be reflected in the copy. Additionally, thinking ahead while creating the base extrude ensured that the mirror plane will be in the middle of the part, allowing me to easily mirror here. The bracket now just needs holes in the base and fillets added to it, and I'll use the next couple lessons to show you a couple different methods to add the holes. So, you know it's possible to use the extrude tool to make cuts and remove material. But if you plan on drilling holes that are a standard size for either clearance holes or hardware, the hole feature can make that process much easier. I'll go ahead and launch the feature from the Modify panel on the 3D Model tab to bring up the Hole Properties dialog box. The reason the hole feature is better for standard size holes is that many hole types are already predefined here in the dialog box. All you have to do is choose the correct hole type, size, and termination behavior. Before I dive into those, however, I'll expand the input geometry options and get started by positioning the hole. I'll first select the face I want the hole to go into, the front face for now, and then I can freely change the hole's position by clicking and dragging the center dot. Additionally, I can snap it to the center point of an arc, circle, or cylinder by selecting the geometry, as well as lock it in place at a precise position by selecting an edge and typing a distance. Since I only set a dimension from one edge, the hole still has a degree of freedom, and I'm able to drag it. But I can fully constrain it by selecting another edge and adding a dimension to fully constrain it. Note as well that multiple holes can be placed one after another by simply clicking the face again, but only the active hole can be positioned by clicking Edge Geometry. For this example, I want to add one hole to the top rectangular face here, so I'll clear the selection in the Position selection box and place a new hole on the face near this right corner. I'll leave the position floating for now and move on to cover the type options. The type is determined by the hole and the seat. The hole type options let you choose if you want to use a simple hole with a single diameter, a clearance hole, which lets you select from standard fastener types, a tapped hole, which adds threads, or a taper tapped hole, which gives a different set of thread options. The seat options then allow you to add a counterbore, spot face, or countersink top to the hole. Note that each of these options will update the preview in the behavior options and that the counterbore seat isn't available with a taper tapped hole. For this lesson, I'll use a simple hole with a counterbore seat, then move on. The behavior is how the final shape and depth will be determined, and the termination options here let you determine the hole's end condition. Selecting distance will add a drill point option and update the preview, while through all will cut completely through the material in the selected direction. The to option brings up a surface selection box and will cut the hole up to the selected surface no matter what updates are made to the design. For this lesson, I'll use the through all termination type. Then use the direction options to make sure the preview arrows are pointed into the part body. To set the dimensions for the hole, I can either click on the dimensions here and type in a value, or click and drag the circles and arrows in the drawing area to change them visually. For this hole, I'll use a counterbore diameter of 10 millimeters, a counterbore depth of 3 millimeters, and a hole diameter of 6 millimeters. The last options in the advanced settings allow you to automatically add an I-mate or extend the start so it cuts through any fillets or geometry that may be above the place the hole was placed on. I'll leave them deselected for now, and finally add the hole. To do that, I can either finish this and start a new hole by clicking the plus icon, or close the dialog box by clicking OK. I'll click OK, and the hole is added to the feature tree, with the sketch used to position it placed inside the feature. Editing either the sketch or the feature will let you change the hole's placement or type and termination options respectively. And as a final note, the standard selected in the dialog box will automatically be pulled into any drawing you make with this feature, which is something I'll cover in more detail later in this course. Sometimes it can be useful to create the sketch for your holes before starting the hole command to help quickly position them. To show you what I mean, I'll hide the existing hole feature by right-clicking it in the browser and selecting Suppress Features. Next, I'll start a new sketch on the top surface of the base. In this example, I want to add 4 holes that are offset 15 millimeters from the 4 corners. And the easiest way to do that is to use the Offset Sketch tool. Since I set Inventor to auto-project edges into the sketch, I just need to select the Offset Sketch tool, select the geometry to offset, and move my cursor to see a preview of the offset. I can either click to place the offset and then dimension it, or dimension it directly from here by making sure the preview is in the direction that I want and then typing the value, 15 in this case. I'll press Enter to add the offset and dimension, and am now ready to use the corners of the offset lines to locate the holes. I'll click Finish Sketch, launch the hole feature, switch to the top view, and then simply select the 4 corners of the offset sketch where I want the holes to go. I'll set the termination to Through All, the hole type to Tapped Hole, and the seat to Counterbore. I'll make sure it has a diameter of 10 and depth of 3. Then choose ANSI Metric for the preset and set the size to 10. I'm satisfied with the preview, so I'll click OK, and 4 holes are added. By using an offset sketch to position holes, I was able to incorporate the design intent of always having holes 15 millimeters from the outer profile of the part. This means that even if the size of the rectangular base's sketch or extrude were to change, the offset sketch and hole positions would also update. The fillet feature is used to break sharp edges on the model, and unlike the extrude feature, does not need a sketch in order to be created, only model edges. I'll click on the fillet icon in the Modify panel of the 3D Model tab, and you can see there are quite a few options for creating fillets. The good news is that most of the time, you'll use the constant fillet type, along with a radius, and for that reason, this lesson will focus on constant radius fillets, and then quickly go over the full round fillet option. For the constant radius fillet, I can select either an edge, a loop, or an entire feature. And for this fillet, I'll select edges. As a rule of thumb, when you're adding fillets to your design, it's usually a good idea to add the fillet features last, and to add larger fillets first before creating smaller ones. This is because Inventor is a history-based modeler, so the order in which you add fillets can have an effect on the final shape, and adding small fillets too early can make it difficult to add larger ones. With that said, I'll start by selecting the 4 vertical edges, and as I pick them, notice that a preview of the geometry appears. Notice as well that I can actually pick edges through the part, saving me the trouble of rotating the part to select edges. What happens if you accidentally select the wrong edge? Well, all you have to do is hold down the Control key on the keyboard and click on the edge again to deselect it. The preview looks good, so I'll set the radius to 5, and all 4 edges update since they're all part of the same fillet feature. If you need the edges to have different radii, you must create a separate fillet feature for each radius. I'll click Apply to finish this feature, and the new fillet feature is listed in the browser. Since I hit Apply instead of OK, the fillet feature dialog box stays on the screen, so I can add more fillet features. This time, I'll switch to the loop option, select the loop that goes around the top surface of the base, and select other loops that are part of the tab shapes. I'll change the radius to 4 to update the preview, and when I click OK, all of the fillets are added. If you take a look in the browser, notice that the fillet features are the only ones that don't have a plus icon next to them. This is because they aren't based on any specific sketch or feature, but rather the existing geometry as a whole. You can still, of course, edit the feature to change its settings, but I'm good with them for this model, so I'll click OK once again. I mentioned I would also go over the full round fillet, but it doesn't fit with this design, so I'll switch to another part to show you how it works. To get started, I'll launch the fillet feature and change the type to full round. The full round fillet is used to create the perfect blend between 3 adjacent faces rather than break an edge. So the next thing I need to do is choose the 3 faces to blend. I'll select one of the sides the center face, and the other side. And when I do, you see I get a perfect blend of all three. Since the full round fillet references the faces directly, if any of the faces were to ever change, the full round fillet would update to make sure the faces still blend well. The Revolve feature allows you to take a two-dimensional profile and revolve it about a center line to create 3D geometry. Revolves are usually based off a 2D sketch that is then revolved around an axis. So in this lesson, I'll use the Revolve feature to create this wheel. Since I'll be revolving the sketch 360 degrees around an axis, I only need to sketch half the wheel, which for this lesson will be the upper half. I'll then revolve the geometry around a center line to create the core of the wheel shape. I'll start by creating a new file with a metric template and start a 2D sketch on the XY plane. Next, I'll use the line tool to create the left half of the sketch. Since I want the right side to have the same geometry, I'll use the Sketch Mirror tool to save some time. I'll select all of the geometry I want to mirror and use this vertical line as the line to mirror across. The preview looks good, so I'll hit Apply and then Done. By mirroring the first side, Inventor automatically adds symmetric constraints to the geometry. So, if I drag the geometry on one side, the other side updates appropriately. To fully constrain the sketch, I'll add a few dimensions. I'll set the distance between the two outer vertical lines to 60 millimeters. The distance between the two inner vertical lines to 30. The distance between one of the lower horizontal lines and the bottom to 25. And the distance between one of the upper horizontal lines and the bottom to 45. I want this revolve to have filleted edges, but instead of adding them as a separate feature later, I can simply add sketch fillets now to get the geometry I want. I'll enable the command, set the fillet radius to 3, and select all the corners I want to fillet. I'll press Enter to add the fillets, and notice that they're controlled with a single dimension. Since I added them all at once, Inventor added an equal constraint between all the fillets, and I can now control them as a group. The sketch is ready to be revolved, so I'll launch the Revolve feature. And for the profile selection, I'll pick both the left and right halves, since Inventor recognizes them as separate profiles due to the vertical line segment here. If I had made the vertical segment a construction line, then Inventor would have seen the shape as one profile. For the axis, I'll select the bottom horizontal line, and the preview immediately updates. The behavior options are similar to those for extrudes, with direction options that you can use to choose the direction of the revolution, revolve in both directions equally, or revolve unevenly in both directions. The distance options are replaced with angle options, and you can use them to specify a specific angle, go through a full rotation, or revolve up to a chosen reference. Since I want a 360-degree revolve for this part, I'll select Full and click OK to create the feature. I want the final part to have a circular hole in the center of it, so I could cut out the hole with an extrude feature, but I want to show you how to add that center hole by adjusting the revolve settings instead. I'll edit the revolve sketch. Add a horizontal line below the bottom of the main geometry and dimension it 10 millimeters below the bottom edge, which will act as the radius of the hole. I'll click Finish Sketch and notice that the model doesn't update right away. Inventor is still using the same options I selected the first time I created the feature. To change them then, I'll edit the feature and clear Axis field. I'll select the new horizontal line as the axis of revolution, and the preview updates with the hole, so I'll click OK. With that, the base geometry of the part is complete. In the next lesson, I'll add a set of circular cutouts to the larger face here using the Circular Pattern tool. To complete this wheel part, I'll need to add some circular cutouts to this face. I'll right-click and start a new sketch on the inner flat face using the marking menu. This will be a simple circular sketch, which I'll replicate later with a pattern. So I'll launch the Center Point Circle tool from the ribbon, click once to place the center, and again for the radius. At this point, I'll press Escape on the keyboard to end the command. For the design intent of this cutout, I want to ensure that the center of the circle is always positioned vertically above the origin. To add that geometric relation then, I'll select the vertical constraint in the ribbon, and then select the center of the circle and the origin. The sketch snaps into place, but if I click and drag the circle, you can see its radius is underdefined, and it's free to move up and down. To define its distance from the origin, I'll launch the Dimension tool from the marking menu, click on the circle and the origin, and then place the dimension. I'll type 34.5 millimeters and press Enter. Before I define the circle's radius, I'll press Escape to end the Dimension tool and show you another way to access it. Inventor remembers the command that you used last. That means that I can access the Dimension tool I just used by right-clicking in the design window to bring up the marking menu. Notice that at the top of the menu, it says Repeat General Dimension. I can click here to enable it, or I can just press the spacebar or Enter key without bringing up the marking menu to automatically repeat the last command. I'll add a diameter value of 9 millimeters and hit Escape to exit the command. The sketch is now fully constrained, so I'll finish the sketch and enable the Extrude command. I want the cut to go through the entire geometry of the wheel, so I'll select the circle as the profile, change the output to Cut, the distance to Through All, and click OK. What I'd like to do now is to replicate this hole using a circular pattern. I can find the icon for a circular pattern in the Pattern panel on the 3D Model tab, and once enabled, need to select the features to be patterned. I'll select the cut extrusion I just made, and next need to set a rotation axis for Inventor. For a circular pattern, this can be a circular face, a circular edge, or even the axis of revolution that was used to create the initial revolve feature. In this case, I'll just click this outer filleted edge, and a preview of the pattern appears. You can adjust the total number of occurrences you want the feature to create in the placement box. I'll choose 12 for now. Similar to the Revolve tool, you can also choose to adjust the angle value. I'll type in 270 degrees, and you can see that the pattern is only extended through 270 degrees. If I click the button next to the Rotation Axis option, I can reverse the rotation's direction. More advanced options can be accessed by clicking this arrow on the bottom. And if the positioning method is set to fitted, like it is now, the number of occurrences will be evenly spaced throughout the angle I set above. If I wanted to choose how far apart each occurrence is from each other instead, I can switch to incremental. With this option selected, I'll change the angle value to 20 degrees, and notice each hole is now equally spaced 20 degrees apart. I'll switch back to fitted and change the angle to 360 degrees so all 12 instances are patterned equally about the wheel. The preview updates, so I'll click OK, and the circular pattern is added. Now that you've seen how to use circular patterns, I want to show you how I could have used a different pattern type, rectangular, to position the holes in the bracket I made in the last section. As you can see here, the holes at the corners were placed as a group with a single hole feature. But if I knew the hole specifications, but not the locations when I first created it, I could have instead created a single hole and then used the rectangular pattern to add the additional instances. I've already created this single hole scenario in this part, so I'll roll the end of part to underneath the suppressed hole feature, then right-click to unsuppress it. For better clarity on the feature positions, I'll also select and suppress the mirror, cutout, and tab features. With the setup done, I'll activate the Rectangular Pattern tool from the Pattern panel to bring up the Rectangular Pattern dialog box. From here, the first thing Inventor wants to know is what feature I want to pattern. If there are multiple solid bodies in this file, I could select the Solid Bodies option here for the pattern source. But in this case, I'll just select the whole, which can be selected from either the design window or the browser. I'll then move on to the direction options, and notice that the rectangular pattern lets me replicate the geometry in either one or two directions. Starting with direction 1, I'll click the arrow button and click on a model edge to define the direction. If the pattern is going in the wrong direction, I can use the button here to flip it. Next, I need to specify the number of instances. Note that this number represents the total number of holes, including the original feature, so if I set it to 1, only the source instance will show. I'll set it to 4 and point out the option here called midplane, which distributes the pattern on both sides of the original feature, weighted towards the direction I specified. If you look at this dropdown, you can see that I'm currently using the spacing option, so the value here controls the distance from one occurrence to another. You can also think of this option as center-to-center spacing. Alternatively, you can switch to the total distance option, which uses the value here for the total length of the pattern and then evenly spaces the specified number of instances throughout that length. Finally, you can space the occurrences evenly along a curve by using the curve option here. For this example, I'll use the spacing option. Set the space between them to 80 millimeters and set the count to 2. With that, direction 1 is set up, and I can create the occurrences on the other side by activating direction 2. I'll click on this model edge to specify the direction. And just like with direction 1, if the pattern is going in the wrong direction, you can reverse it with this button. Here, I'll set the count to 2 and the spacing to 130. The preview updates, and notice how the pattern for direction 2 is copying the occurrence from direction 1, not just the source. I'll click OK, and the pattern feature is added. A quick note about the design intent here. When you use the pattern feature, all of the replicated geometry is driven by the original feature, while the pattern controls the spacing and number of copies. So, if the overall shape of the part were to change, the original feature will be correctly positioned, but the replicated holes will still be driven by the outdated pattern parameters. Notice as well that if I unsuppress the tab, cutout, and mirror features, they're repositioned appropriately since they were created with symmetry in mind. It's always important to consider what the design intent is when choosing an approach to get the geometry you want. Once individual parts are created, they can be brought together in an assembly file to create a more complex model. By putting parts together, it's possible to identify and correct design problems that may not have been noticeable at the part level, as well as get a bigger picture of how the parts will be used in the real world. Since assemblies are primarily used to associate parts from multiple files in a single environment, it is very important that the parts and assembly files stay grouped relative to each other. This is because the assembly file looks for the part every time it opens. So if the part isn't there, then it can't be loaded into an assembly. Everything can be moved as a group though, as long as the same relative location, such as the assembly being in the same location as a folder with all its parts, is maintained. And you can use Inventor's Pack and Go command to quickly pull together files that can be sent as a group. To begin an assembly file, I'll click on the new icon and select the standard metric assembly template. When the blank assembly file opens, you'll see there's a new tab on the ribbon called Assemble, but otherwise, the assembly interface looks mostly like the part interface you've seen so far. I have the ribbon and panels, the browser, and the design window. Next, I'll take a look at how to bring parts into the assembly, how to put them together, and how to test mechanisms for fit and function. Once you have an assembly file open, there are 3 different ways to insert an existing part into an assembly. Certain methods may be more useful in certain situations, but I recommend you practice using all the methods shown in this lesson until you develop more experience and learn which works best for you. The first method for placing components is to use the Place command from the Component panel. I'll select it, and the Place Component window appears. From here, I can browse for a file to place in the assembly, as well as look for specific file types with this drop-down filter. If I leave it set on Component, Inventor will filter for only part and assembly files. Once I find the file I'm looking for, the bracket, I'll select it and click Open. To insert the part, I could click to place it in anywhere in the design window, or I can attach the assembly to the origin by right-clicking and selecting Place Grounded at Origin. For now, I'll just click to place it here. Notice that Inventor keeps a preview of the part attached to the cursor, which lets me add more instances of the part. This can be a time saver, so you don't need to constantly relaunch the command, but I only need one instance in this example. So I'll press the Escape key on the keyboard to finish the Place command and use the View cube to get an isometric view. The second method for bringing in a component is to drag and drop it from another Inventor window, meaning you need to already have it open. I already have the pin part open, so I'll tile the windows vertically to see both files. And notice that when I click in each window, that the browser switches to show the part or assembly tree. In order to drag the part into the assembly, I'll make sure the part window is active and drag the parts icon from the browser, not the parts design window, into the assembly design window. Of course, if you need multiple instances of the component, you can simply keep dragging it in from the browser. With the pin added in, I'll maximize the assembly window and go over the third way to insert a part into an assembly, by dragging it in directly from Windows Explorer. I'll bring up an Explorer window showing the part I want to bring in, the wheel in this case, and then simply drag and drop it into the design window. This method is great since you don't need to have the part open in Inventor and you can quickly add multiple parts at once. Once a part is in the assembly, notice that each instance of it appears in the browser, similar to how features were listed in a part file. I can create another instance of any component shown here by dragging and dropping it from the browser, as well as get rid of any extra instances by clicking on it to highlight it and pressing Delete on the keyboard. Since assemblies simulate how parts fit together and move in the real world, and all three of the parts I have here are free to be dragged around the screen and moved to look like they're put together. If I change views or move a part again, it's clear, however, that they're still just floating in the 3D space here. To better simulate real-world interactions, I'm going to need to set one part in the assembly to have its location in space fixed, and then connect all the other parts relative to it. For this assembly, I want the first part I brought into the assembly, the bracket, to be the fixed component, which in Inventor terms, that means that I want it to be grounded. Think of the first component like the chassis of a car, where other components, including moving components, are assembled to it to make a full working vehicle. You need one item to be fixed in 3D space so the other components have a frame of reference to move about. Since the bracket wasn't grounded to the origin when it was placed, I can ground it by right-clicking on the part and selecting Grounded. In the browser, there's now a pushpin icon next to the name, indicating that the part is grounded. If I need to free the part and allow it to move, I can right-click again and deselect the grounded option, but for now, I'll leave it as is. The other two parts still have degrees of freedom and can be moved around using the Free Move tool on the Position panel by simply clicking and dragging on them, or by enabling the Free Move tool first with the hotkey V. Parts can additionally be rotated by using the Free Rotate tool, which you can enable from the Position panel, or by pressing the hotkey G. With the Free Rotate tool enabled, I can select a component and then rotate the part freely by clicking and dragging it, or in a specific orientation by clicking and dragging on either the circle or axes shown here. While the Free Move and Free Rotate tools are helpful for getting parts close to a desired location, they don't have the precision needed to properly assemble everything. So, even though I'm able to roughly position components, they're not connected in any way. To connect them, and more accurately represent real-life movement, I'll need to use something called constraints. Think of assembly constraints as the 3D version of sketch constraints. They're tools that create relationships in 3D space between components, such as making two components flush, concentric, or tangent with each other. Inventor has several different types of constraints that you can use, and each one can remove degrees of freedom from components in specific ways to imitate real life. The most common way to add constraints is with the Constrain tool, which is found in the Relationships panel of the Assemble tab. Clicking it will bring up the Place Constraint window, where you can define how two parts will be constrained with each other. While there are 4 tabs in the window, I'll only focus on the Assembly tab for now, since it contains the most frequently used constraint types: mate, angle, tangent, insert, and symmetry. In this lesson, I'll focus on the powerful and versatile mate constraint. To get started, I'll constrain the hole in the wheel to the cylindrical hole in the bracket. When making selections, Inventor lets me use points, edges, faces, axes, and planes. But since I want to mate a pair of holes, I can either hover over one of the cylindrical faces to select the axis, or the circular edge to select the actual edge. In this case, I want the two axes to line up, so I'll be sure to click on the cylindrical faces of each hole. And as soon as I make the second selection, the wheel component snaps into place. I'll click Apply to add the constraint, and notice that the Place Constraints window remains active, which is nice because it usually takes more than one constraint to assemble components. With that said, I'll close the window for now. And if I click and drag the wheel, notice I can only move it along the cylindrical axis of holes or spin it. This is because with the constraint I added, I've only locked down 1 degree of freedom. This is the basic approach to assemblies. Bring in a part that is completely free to move in space, then add constraints to restrict this movement until it behaves as you want. To finish constraining the wheel, I'll once again click Constrain, and next need to center the wheel between the 2 tabs on the bracket. There are a few ways to do this. One approach is to click on one of the faces of the wheel, like this protruding face, and then the flat face of the bracket. You can see this mates the 2 faces together, which I can see better by looking straight on with the assembly. If the alignment is not what I was expecting, I could use the solution buttons to flip the alignment so the components are either mated to each other or flush with each other, and I'll use the mated solution for this constraint. I want the wheel centered in the bracket though, not stuck to one side, so I'll need to do an offset to the constraint before I add it. The spin box here can accept either positive or negative values, but before I commit to a value, I need to ask what would this do for the design intent. Well, if the bracket were to ever change width, then the wheel would no longer be centered. It would just be offset from this face by an exact value, meaning I'll want to take a different approach. When these parts were designed, I incorporated symmetry around the default reference planes of each of these parts. I can now take advantage of those reference planes when adding constraints. To do this, I'll make sure the first selection box is active in the Place Constraint window, then expand the bracket in the browser as well as its origin folder. Now, when I hover my mouse over the planes in the browser, I can see a preview in the design window. And for this mate, I'll select the XY plane that runs through the center of the bracket. If I didn't have these default planes here, I could always create new planes to mate. As you become more experienced, you'll find yourself thinking ahead as you design parts to make sure the reference planes end up in places where they'll help you at the assembly level, like this example. I now need to mate the wheel part, so I'll make sure to click the second selection box and then expand the origin folder for the wheel part and select the YZ plane that runs through the component center. As soon as I select this second plane, the component snaps into place. And notice that each plane's highlight color corresponds to the selection button's colors. If I again look straight on with the assembly, you can see the wheel is centered within the bracket. Because of the design intent incorporated with this approach, if any components get wider in the future, they would still remain centered here. I'll click Apply, and at this point, all I have to do is insert the pin. In the previous lesson, I constrained the wheel part to the bracket, so now I have to constrain this last free-moving part, the pin. To do this, I'll once again bring up the Place Constraint window, and with the mate type active, Select the pin and bracket cylindrical faces so the pin snaps into the hole. I'll click Apply, and now when I try to move the pin, you can see it's still free to move along its axis, so I'll need to add another constraint. For my design intent, I want to constrain the pin so the hex head is flush to the bracket. So I'll move the pin away from the bracket so it's easier to click, and toggle the selection buttons to reset the selections. For the first selection, I'll choose the circular edge on the pin where the bolt and cylinder meet. I'll then orbit the part so I can see the face on the bracket I want to mate it to, and click on the outer circular edge of the hole. The pin snaps into place, so I'll click OK to accept the constraint and close the window. Before concluding this lesson, I want to point out that all of the added constraints are listed here in the browser. And if I hover over them, you can see they highlight in the design window. As you might expect, these constraints can be edited or deleted, just like features you've seen up to this point, by simply right-clicking a constraint and selecting Edit to bring up a similar Edit Constraint window. In the previous lesson, I added two mate constraints to the pin to define its position, but notice that it can still rotate. Inventor has a few ways to lock the rotation for this component, and in this lesson, I'll show you two approaches, adding an angle constraint and replacing a mate constraint with an insert constraint. Since I can add an angle constraint on top of the mates I already have, I'll start with that option and click Constrain once again. Then switch to the angle constraint in the Type section. This constraint adds an angle between edges or faces and has three different solutions used to determine orientation. To lock the rotation, then, I can make one of the bolt faces parallel to the bracket's top face with a simple angle. Before creating the mate, I'll choose the directed angle solution, since I'm only working with two selections, and then select one of the bolt faces and the bracket's top face. The preview updates, and you can see that the faces are parallel in the same direction, noted by the arrows. Alternatively, I could type 180 degrees in the angle input box to orient the faces towards each other. I'll click OK to add the constraint, and now when I try to rotate the pin, it stays firmly in place. I'll click Undo to delete the angle constraint and let the pin rotate again. This time, I want to lock it using an insert constraint, which is specifically intended to position cylindrical components like screws and bolts into holes. The insert constraint sort of kills two birds with one stone by aligning the cylindrical axes and the end faces of the parts in a single step. I'll expand the pin in the browser and remove both mate constraints so that it's free to move. And once again, bring back the Place Constraint window. In the Type section, I'll select Insert and then click the two cylindrical faces to mate, and use the Align solution to make sure they're oriented correctly. Notice when I look straight on, though, that the bolt isn't flush with the bracket. This was due to me selecting the cylindrical faces. In order to make the bolt flush, I'll need to instead select the circular edges on the pin and bracket that I want touching. To fix that, then, I'll restart the Constrain tool, make sure I have the type set to Insert, and then rotate the assembly as needed to select the circular edge on the pin that will be touching the bracket and the outside circular edge on the bracket. I'll make sure the solution alignment has the pin positioned correctly, and to ensure the rotation is locked, I can simply check the Lock Rotation box on the bottom of the window and a lock icon appears on screen. With the preview correct, I'll press OK to add the constraint. The Insert constraint now appears in the browser, and because I lock the rotation, the pin is immobile when I try and rotate it. The insert constraint can definitely save you time if you have hardware or other cylindrical components in your design. And if you ever need to change the constraint's offset distance to add a gap, you can do so quickly by clicking on the constraint in the browser and changing the value in the pop-up. Since parts in an assembly only simulate real components, it's possible for two or more components in an assembly to occupy the same space, even though that would be physically impossible in the real world. To detect such errors, Inventor provides a tool called Analyze Interference, which can be found on the Inspect tab of the ribbon. I'll click on the icon to bring up the Interference Analysis window, And you can see that I now need to define two selection sets. Each set can contain as many components as you want, but each set requires at least one component, and a component can only be in one set. This is because Inventor will compare the two sets as a whole and then identify areas where the sets overlap with each other. These highlighted areas then show you areas that you need to look at to fix your assembly before manufacturing. But keep in mind there are instances, like that of a press fit, where some interference is necessary. For this assembly, I'll select the pin for the first set, then click on Define Set 2 and select the bracket and wheel. I'll click OK to run the analysis, and once it's done, a message window appears, letting me know there is an interference between the pin and bracket. The interference is highlighted in red in the drawing window, but note that if no interference was detected, a simple pop-up would appear letting me know that, and the tool would close. Since there is interference, however, the message shows me the total volume of the interference, and I can expand the window to display even more information about it. I'll click OK to close the message window, and in the next lesson, I'll make a design change to fix this problem in the part file and show you how the change automatically takes effect in the assembly. In the previous lesson, I used interference analysis and found that the hole in the bracket is slightly smaller than the pin. To fix this, I'll make a change to the hole size in the bracket directly from here in the assembly file without the need to open the part file. To show you how this is done, I'll double-click anywhere on the bracket, and I'm brought into part editing mode. The rest of the assembly components immediately become ghosted, and the feature tree expands in the browser so I can make changes, just like in the part environment. The cut extrusion in the bracket that I want to change is controlled by a sketch. So, to make the hole a bit larger, I can click on the hole's cylindrical face and select Make Sketch Visible from the pop-up. From here, I'll change the dimension by double-clicking it and then setting the width to 20 millimeters. To return to the assembly, I just need to click the Return command in the ribbon. The assembly automatically updates, but if you want to make sure that the change is implemented into the assembly, switch to the Manage tab on the ribbon and click Update. I'll then go to the Inspect tab and Analyze Interference once again. I'll select the pin for the first selection and the wheel and bracket for the second. Now, when I run the analysis, no interference was detected, so I'll click OK. Remember, even though I'm in the assembly file, this change was actually made to the part itself. To prove that, I'll open the bracket up in its own window by right-clicking on the component and selecting Open. I'll then edit Extrusion 3's sketch, and you can see that the diameter is indeed 20 millimeters. This associativity works in both directions, so any changes that I make here in the part file will appear in the assembly when I update it, which makes sure that all associated files are always current with the latest changes. This will become even more important when I start talking about drawings, but for now, I'll move on to discussing contact sets, which serves as another way to simulate interaction between components. Up to this point, I've used constraints to position components and simulate their actual motion in an assembly. But keep in mind, the constraints are only a simulation of the assembly, not a true physical interaction between faces of components. In cases where you do want to create a true interaction between components, you can use something called contact sets. To show you how this works, I'll first suppress the constraint between the planes on the wheel component by expanding the wheel in the browser to show its constraints, then right-click on the Insert constraint and select Suppress. This will remove the constraint's impact on the assembly, as if I deleted without the need to actually delete it. That means that if I ever want it back, all I have to do is unsuppress it. I'll click and drag on the wheel, and you can see that with the constraint suppressed, it's free to move along the axis and interfere with the bracket. I want to use contact sets to prevent this interference, so I'll make sure it's between the tabs of the bracket and then right-click on the component in either the browser or graphics area and select Contact Set. A new icon pops up next to the part in the browser to show that its contact set is enabled, but only enabling one won't have any impact. To get the results I'm looking for, I'll need to repeat this for the bracket, and again you can see the icon appears next to the component in the browser. At this point, if I try to move the wheel, notice the contact sets have no effect. I still need to tell Inventor to take the contact sets into account. To do this, I'll switch over to the Inspect tab and notice there's a button to activate Contact Solver. I'll activate it, and now when I move the wheel, you can see that it won't interfere with the bracket as it's moved. Additionally, if I unground the bracket and move the wheel into it, you can see that the bracket actually moves when the wheel runs into it. This can be a huge advantage when you want to verify how certain components will interact in the real world. But due to the amount of computer resources required, it can drastically slow down your machine, so I recommend only enabling it when you need it. In most cases, constraints do just fine for simulating the position and interaction between components. But when you want to see what the true physical interaction between components will be, contact sets will give you the most accurate results. Exploded views are generally used when it comes time to document assemblies and communicate how the components are put together. In Inventor, they're both used to animate how an assembly goes together and to document an assembly in traditional 2D drawings. Now, most people are used to using the term exploded view, but there actually is no explode command in Inventor. Instead, exploded views are actually created in a separate file called a presentation file. By using a separate file, you can freely move components that would otherwise be constrained in the assembly for visualization purposes. To get started, I'll select the New File icon, and then select a metric presentation template noted by a .ipn file extension. When I click Create to being the presentation file, a dialog box appears, asking me to select an assembly file to insert. Instead of selecting one right away, however, I'll first exit this dialog box and save the presentation file to help me avoid problems with the links between the assembly and presentation files later. Next, I'll click the Insert Model button, find and select the assembly I'd like to explode, and click Open. You can now see the assembly here in the presentation file, along with new tabs on the ribbon, a Snapshot Views panel on the right, and a Storyboards panel on the bottom. To explode the assembly, I'll be using the Tweak Components tool found on the Presentation tab. I'll enable it, and the mini toolbar that pops up will help me select which components to explode, along with the direction to explode them. Before I select anything, I'll make sure the default trail option is set to All Components so that the explode lines are created automatically. As I hover my cursor over the model, you can see faces and edges highlight. I'll select the circular face on the pin as a reference, and a triad appears. I'll click and drag one of the arrows and slide the pin component out of the hole. To continue exploding other components, I'll press the green check to finish the first tweak, and then reselect the Tweak Components button. This time, I'll click on the wheel and use the arrow to move it up. Notice there's a place where I can type in a value for an exact move, but most of the time this is a pretty visual process. At this point, I'll click the green check. And notice that a Tweaks folder was added to the browser. I'll expand it. You can see each tweak I made. If I wanted to adjust one of the tweaks after it's been created, there are a couple of ways I can go about it. First, in the working area, notice the trailing lines. If I click on one of them, a green drag handle appears that I can simply click on and move. Alternatively, I can directly edit a tweak's value by clicking on it in the browser and typing an exact distance. To show the mini toolbar with all the options again, I can just double-click on the trailing line. If I wanted to show or hide the trailing lines, I do so by right-clicking on a tweak in the browser and selecting Hide Trails. To return a component to its original position, I can just delete the tweak by either right-clicking on it in the browser and selecting Delete, or by selecting a trailing line in the working area and pressing Delete on the keyboard. If any changes need to happen to any of the parts or in the assembly file, all of the files are linked here. So any and all changes will propagate to this presentation file so that it reflects the latest and greatest version in the exploded view. Later on, in the drawing section, I'll show you how to work with presentation files like this in order to document your assemblies in 2D. To make complicated subassemblies a bit easier to work with, Inventor allows you to create something called subassemblies, which are created when you insert an existing assembly into another assembly. Once inserted, they can be constrained and positioned just like parts. So, in this lesson, I'll create a new assembly using this base plate and then add the pin, wheel, and bracket assembly to show you how to work with subassemblies. I'll go ahead and select the new icon and select an assembly template. I'll insert the baseplate component by tiling my open documents and dragging the baseplate from the browser to the new assembly window. Next, I'll insert the completed pin, bracket, wheel assembly by clicking on the place icon and browsing for the assembly. I'll open it and can now simply click to place it in the desired location. Inventor keeps the place command open, so I can easily click to place 2 more instances in the window. I'll press Escape to exit the place tool, and just like with parts, can insert more copies of the subassembly by clicking and dragging from the browser. One of the advantages of using subassemblies is that these components retain the constraints that were used to initially create them, saving you the trouble of reconstraining each instance and making it much easier to insert into higher-level assemblies. To position one of these subassemblies, I'll click the constraint icon and create a mate between one of the edges of the holes on the subassembly. And one of the edges of the holes on the base plate. I can then repeat this for the cross corner and finally add a mate between the bottom face of the wheel subassembly and the top face of the base plate to finalize the subassembly's position. Now that you've learned tools to create parts and assemblies, in this next section, I'll show you how to document those models with 2D drawings. Drawings are one of the 3 main file types you can create in Inventor and are used to document your 3D models in the traditional 2D format, which includes displaying dimensions and other instructions useful for manufacturing purposes. In Inventor, creating drawings is secondary to creating 3D models of parts or assemblies, which means that you first create models in 3D and then use the 3D data to generate the drawing. The drawing then has a direct association to the 3D model, similar to the link between parts and assemblies, such that when changes are made to the model, each and every view in the drawing will reflect the change. This relationship between 3D model and 2D drawing makes the drawing process fast and accurate. To begin a new drawing, you can use the icon in the New section of the home screen, use the New drop-down menu, or use the blank page icon to bring up the New File dialog box. From here, you can choose templates that use either English or metric units, and then select the drawing file you want from the right. Inventor drawing templates are the ones with the .idw file extension, and you should be aware that templates that use the ANSI standard will use third-angle projection in the drawings, whereas ISO or DIN will use first-angle projection. I'll select an ANSI Inventor drawing file for now, and a new file opens using the Inventor drawing interface. It is laid out similar to the part and assembly interfaces, with a work area, a browser, and a ribbon. But notice that the ribbon uses slightly different tabs that are more appropriate for 2D drawings, such as placing views and annotations. The browser is also arranged a bit differently. Since I'm no longer working in 3D, you won't see reference planes or an origin listed. Instead, there are basic requirements for a 2D drawing, a sheet of paper listed as Sheet 1, and drawing resources with things like sheet formats, borders, title blocks, and symbols. I'll take a look at these items along with the various commands on the toolbars throughout this section of the course, but before I do, here's a short disclaimer. The specifications for drawings vary immensely from company to company and individual to individual. For the remainder of this section, I won't be teaching you how to create one specific standard of drawing. Rather, I'll teach you the tools and techniques required to create and detail drawings in general. This will allow you to produce your style of drawing, no matter how unique the specifications. Once you've started a new drawing file, one of the first steps is to insert the first view of your model, known as the base view, which will be the view that several other types of views are based on. I'll select the base icon on the ribbon, and a dialog box appears. On the Component tab, Inventor wants me to select the 3D model to put in the drawing. The drop-down contains a list of Inventor files that I currently have open in other windows. If the model I want to add isn't listed here, I can browse for a different file on my hard drive or network location. I'll use this bracket part for my base view. Once a file is selected, take a look over at the view cube. By rotating it, I can specify the orientation of the 3D model I want for the base view. This is nice, since there may be times where I want the front view of the drawing to be the right view of the part. For now, though, I'll leave the view cube set to Front. Back in the dialog box, I can use the Style section to choose how I want the view to appear on the drawing by selecting Hidden Line Removed, or Shaded, as well as choosing if the view is a raster view or not. I can also adjust the label and scale, but I'll come back to these options, as well as the other tabs in the dialog box in later lessons. Before I exit out of the dialog box, though, there is one last thing I want to mention. Inventor automatically lets me place projected views from the base view command once I've placed my base view. This is very helpful, as the most common next step is to add projected views, but I'll be going over them a bit more in the next lesson. I'll click OK, and the base view is added to the drawing. Projected views are 2D drawing views created from a parent view. They use the same model as a base, but rotate it to a set orientation based on the direction the view is projected in. The parent and projected views share some properties by default, such as style, and will automatically stay aligned. As you saw at the end of the last lesson, it's possible to add projected views when adding a base view, but if you decided not to add any projected views immediately, it's easy to add them in with a separate tool later. Since this drawing already has a base view, all I have to do is select the Projected View command on the ribbon, and then select the view I want to project from, the front view in this case, and move the cursor in the desired projection direction. When the view is where I want, I'll click, and as I move away, notice that a box appeared showing where the view will be placed. I can continue projecting other views from the parent view I selected, and when I'm finished, I'll right-click and press Create. The boxes are filled with the views I wanted, top, right, and isometric, and since they were created in relation to the front view here, when I hover over its border, then click and drag to move it, the projected views stay aligned. Notice as well that the view I projected up from the parent can only be moved up and down, and the view I projected towards the right can only be moved side to side. But the isometric view can be moved freely. One of the more common views used in 2D drawings is the section view, which can show the internal structure of parts that might not be visible from a standard orthogonal or isometric view. Like a projected view, it needs a parent to be in place, but once that has been added, creating a section view in Inventor is straightforward. To start adding one, I'll go to the ribbon and select the Section tool. With the command now active, I first need to tell Inventor which view to draw a section line through. I'll select this front view, and when I do, the cursor changes, and I'm prompted to enter the endpoints of the section line. This line will determine where the view is cut for the section, and in this case, I want to create a section view that cuts through the center of the part. Notice as I move the cursor over the different geometry in the part, specific reference points are highlighted. These make it possible to cut the part exactly how I want. And when I hover above the middle of the part, an inference line appears, indicating that this is the part's center line. I'll use this inference line as my reference and place 2 points to section the part down the middle. Once the line is sketched, I'll right-click and select Continue. As soon as I do, a preview of the section view appears, along with the dialog box. As I move the preview from side to side, notice that the section line changes its orientation, meaning the side that I place the view on will have an impact on its appearance. In the dialog box, I have control over some options, such as the view identifier label and scale, the appearance style, the section depth, whether or not to include a slice, the method choice, and how I want the cut edges to appear. I'll leave these options at their defaults for now though, and to complete the view, either click OK or simply click the left mouse button on the drawing sheet to drop it in place. Once the section view is created, you can move it, but notice that it will remain aligned to the view it was generated from and won't switch orientations when I move to the other side of the parent view. If you want to edit the section view after placement, you can do so by double-clicking on the view's border to access the section view dialog box once again. When a view contains small features that are difficult to see in a standard drawing view, a detail view can be used to zoom in and make things clear. To create a detail view, just click its icon on the Create panel and select the view that you'll create the detail view from, such as this top view. When I do, a dialog box appears, and I'm prompted to select the center point for the fence or area that the detail view will zoom in on. Before I select the point on the sheet, though, I want to talk about a few of the options in the dialog box. The view identifier lets me change the label for the detail view, and I can change the scale, as well as the styles I want to use for the view. Below that, the options here give me some control over the shape of the fence and the cutout of the final view. Before I draw the fence, I'll make sure its shape is set to circular, then click anywhere on the sheet to establish the center, and move out so a preview appears. At this point, you can see how the fence shapes affects what's included in the detail view. I'll click again to place the circle that defines the fence, then make sure I have the cutout shape set to jagged in the dialog box, and click one last time to place the view on the sheet. Once placed, I can still change the area displayed by the view by clicking on the circle used to create the view, and then dragging to change the circumference of the circle. To move the circle and change what the view is centered on, I can click and drag the center point of the circle. As I do this, notice that the detail view will update immediately to show you the result. Notice as well that Inventor also took care of adding the view identifier and the view scale underneath the detail view. If for any reason you want to change the nodes here, just double-click on them and make any changes you need. Keep in mind that text format dialog boxes often include certain model properties in angled brackets, like you see here. So, if you want to keep those properties, make sure to add the text outside of these brackets. Once you've got some views added into your drawing, Inventor has several ways to add dimensions to detail them. I'll switch to the Annotate tab on the ribbon, and you can see that there are several dimension tools available. Before I start using them though, I want to point out that one of the advantages of creating all of the 3D geometry first is that many of the dimensions you might need for the 2D drawing are already contained in the 3D file. You just need to retrieve them. I'll click the Retrieve Model Annotations icon further down on the ribbon to bring up the Retrieve Model Annotations dialog box, and can then simply select a view where I want the dimensions from the 3D file to go. For this lesson, I'll click the top view here, and all the dimensions that can be seen in this view appear. I can click OK to add all of the dimensions for the part, or select individual dimensions to keep. In this case, I want them all, so I'll click OK, and the dimensions are added. This saves a step of manually adding the dimensions yourself, but you usually have some cleaning up to do. To move the dimensions, you can either click on the dimension text to move it, or the green dots that serve as drag handles. As I rearrange the dimensions in the view, you can see that some dimensions, like the dimension for the extruded hole, would actually be clearer if they were shown in other views instead of this one. To move it to another view then, I'll right-click on the dimension, select Move Dimension, and then just click on the view where I want to move it, the front view in this case. The dimension then attaches to the feature in the selected view. And note that retrieved dimensions, such as these, can only be shown in one view at a time. If you want to show in multiple views, you can always recreate the dimensions yourself manually using the Dimension tool. This tool works the same way as the Dimension tool used when making sketches in a 3D part model. Just click on an item you want to dimension, and the tool adds the appropriate dimension type. The Retrieve Dimension tool can save you some time, but you'll often need to use the Manual Dimension tool to detail your 2D drawings appropriately. This is because you may have incorporated a particular dimension scheme in your 3D part to give it a specific design intent for controlling the 3D model, but that may not be the best dimensioning scheme for a 2D drawing. A good dimensioning scheme for proper 3D design intent might lead to tolerance stackups or poor inspection dimensions when you try to use them on your 2D drawing. Since Inventor is parametric and has full associativity between the 3D model and drawing, you can have confidence that the dimensions shown in your drawing, no matter how they're added, will always match the 3D model, even if design changes are made. Besides adding dimensions, another common task when working with drawings is adding annotations, such as notes, hole callouts, and tolerances. Each type of annotation has its own tool that can be found under the Annotate tab in the ribbon. For this lesson, I want to start by adding a note annotation, which I'll do by using the Text tool, located in the Text panel of the Annotate tab. To add a note into the drawing, I'll simply click the icon, and notice that my cursor has now changed to a crosshair. I'll then click on the drawing sheet to position my note, and in the Format Text dialog box that appears, I'll add a note that says all fillets 4 mm unless otherwise specified. I could use the rest of the options here to set specific formatting options, but for now, I'll press OK, and the note is added. Notice that the Text tool remains active, so I can continue adding notes or hit Escape on the keyboard to exit. To edit the note, I can simply double-click on it to reactivate the Format Text dialog box, where I can change both the text and formatting freely. Outside of the dialog box, I can additionally click and drag the text to move it anywhere on the sheet. Another annotation tool that I'd like to show you is the Hole and Thread tool. I'll select the tool from the ribbon, click once to select a hole, and click again to place the hole callout. This callout is driven by information from the hole feature used to create the geometry in the part file, and as you can see, contains all of the specific information about the hole. All of the annotation tools are pretty straightforward and easy to use, so I recommend practicing with them in order to become more familiar with Inventor's capabilities. Creating assembly drawings is much like creating part drawings. You can add views, retrieve or add dimensions, and add annotations using the same tools you used when working with parts. To add a base view of an assembly then, I'll click the Base View button, browse to the assembly file I want to create the drawing for, choose the orientation and scale, and place the view. Since I'm now working with assemblies though, there are a few specific items that I'll be covering in the next few lessons that help add clarity to your assembly drawings, starting in this lesson with the exploded view. As you saw in the assembly section of this course, there's actually no command in Inventor called explode. Instead, exploded views are created in a separate Inventor file called a presentation file. For information on how to create these, see the Exploded Views lesson in the Assembly section of this course. Once you have an Inventor presentation file, or IPN file, all you have to do is add a view of it to the drawing, just like with any other base view. To show you how it's done, I'll select the base view icon once again, and this time I'll browse for an IPN file. As I add it, I want to point out a key factor here. I have a base view from multiple files in one drawing. This is important because it allows for greater flexibility when creating documentation, since you don't need to restrict yourself to a single file. For example, I could create a second sheet in this drawing file and add detailed dimensions or manufacturing instructions for specific parts, no matter the file I need to pull them from. In assembly drawings, you often, if not always, need to document the bill of materials, which is a list of all of the different components and their qualities in an assembly. Since Inventor already knows how many instances of a component are in the assembly, it can automatically create this list in your drawings by using the Parts List tool. The parts list created by this tool is a representation of the bill of materials, or BOM, is editable and lets you make changes to it without worrying about any unintended effects on the actual assembly. Creating a part list in Inventor is easy. All you need is a view of the assembly. In this drawing, I have an isometric view, as well as an exploded view from an Inventor presentation file, but any view will work just fine. From the Annotate tab, I'll select Parts List, and the dialog box appears. Next, I need to select the drawing view of the assembly I want the parts list of, so I'll select the unexploded isometric view. Back in the dialog box, I could use the BOM settings and properties options to customize how the parts list is displayed, but I'll leave them at their defaults for now and click OK to confirm the settings. If the BOM table is disabled in the referenced assembly, a dialog box will appear like it's doing now, letting you know that Inventor will enable it for the drawing. I'll click OK to enable the BOM view and click anywhere on the drawing to place it. With the parts list added, you can see much of it is filled out for you automatically. This is because of the linked attributes between the assembly BOM and file properties that drive each cell in the table. For example, the part number column here is driven by the Inventor file name of each component, and the description is linked to a specific file property for each component. Watch, if I switch to the pin component, I can go to its properties from the Inventor menu, and on the Project tab, I'll type in a description. Click Apply, and close the window. Now, when I return to the assembly drawing, the field is filled in on the parts list. Unlike other columns, the item numbers and quantities are driven by the actual bill of materials contained in the assembly file. If you need to make changes to the actual bill of materials, then you can right-click on the parts list you placed in the drawing and select Bill of Materials from the options. Be careful though, as any changes here will affect the actual structure of the assembly. If you want to edit the way the parts list is depicted on the drawing without affecting the actual assembly, you should instead right-click and select Edit Parts List, or double-click the parts list. Here, you can do things like reorder components in the list, override item numbers, or even add items in the table. But all of these changes to the parts list will only affect what is seen here in the drawing. Let me show you. I'll right-click on the parts list and select Bill of Materials. This opens up the master bill of materials from the assembly file, and you can see it's still intact. Once you've added a parts list in your drawing, balloons can be used to tie the information in the table to the parts in the assembly. Because balloons are a type of annotation, the tool to make them can be found on the Annotate tab. By clicking the drop-down here, you can see there is an auto balloon tool as well, but I'll just go over the regular balloon tool for now. Once the command is selected, the pointer will show a small plus sign next to it. All I need to do now is click on an edge of a part in the drawing view, and a balloon will appear with the appropriate item number. I'll click again to place the balloon. And notice when I do that, the leader line continues. This lets you add jogs to the leader line, but I want to finish it here, so I'll right-click and select Continue. After the balloon is added, Inventor keeps the balloon tool active, so I can continue adding balloons to the other components. I'll select another component, click again to place the first point, and this time I'll add a jog, then right-click and select Continue. I'll finish up by adding the balloon for the last component, and since the balloon numbers are linked to the item numbers in the parts list, I never have to worry about them not matching up, even if changes are made to that list. To deactivate the balloon tool, I'll press Escape on the keyboard. If I want to reposition the balloons, I can simply click on them and use the green dots as handles to move them anywhere I wish. If I move the arrow from an edge to the face of a part, notice how it changes to a dot. If I want to add a jog to the leader, I can right-click and select Add Vertex Leader. I can then simply click on the leader to tell Inventor where to add the vertex, and click on the vertex to move it, and add the jog. Inventor also has the ability to change the shape of the balloons. To do this, just double-click on the balloon you wish to change to bring up the Edit Balloon dialog box, and then activate the Override Shape checkbox. As you can see, you can choose from a variety of balloon shapes, and even choose to have no balloon shape at all. Notice as well that from this dialog box, you also have the ability to override the value displayed in the balloon. For this example, I'll leave these options at their defaults, and click OK to exit the Edit Balloon dialog box. One of the nice things about Inventor as a parametric CAD system is that it maintains associativity between parts, assemblies, and drawings. This can save you a lot of time when making drawings, simply because you don't have to create any of the line work used to make each of these views, as Inventor can automatically create views from the 3D CAD model of the part. However, the associativity goes even further beyond that. I'll zoom into this view here, and can then edit any of the driving dimensions simply by right-clicking, selecting Edit Model Dimension, and adjusting the value in the dialog box. I'll increase the rectangular length dimension from 150 millimeters to 200. And you can see that the view automatically updates, along with all of the other views on the drawing sheet. Going further, I can open the part from within the drawing. I'll right-click on the part in the browser and select Open. When the part file opens, you can see the dimension updated here as well, due to the associativity between the drawing and part. If the part is referenced in an assembly, it will update there as well. I'll adjust the dimension value back to 150 millimeters. And when I click Finish Sketch, you can see that the part returns to its original size. Now, when I switch back to the drawing, you can see that the dimension automatically updates here as well. This type of associativity is extremely helpful because whenever you make a design change to the part, you only need to make it once in any location, and it will update anywhere that references that part.